All right, welcome everybody. This is Fred Schenkelberg, and thanks for joining for today's webinar on stress screening. It's not a huge topic, and it's not one of the most popular topics. When a couple months ago we did one on sample size, and we maxed out my meeting room capability, my webinar program. Yet this is one that does occur, and it's one that is common. I've seen it in so many different organizations, and apologize for the phone ringing in the back, but that happens occasionally, as you know. And what we're going to talk about is some of the best practices, some of the good things around doing stress screening, and when and why you shouldn't do it. I'm to be upfront. Yeah, stuff happens, right? Stress happens, and our products experience stress. We talked about that last month with environmental induced stresses. It's just the nature of a product being used is that elements of it are uh, impinged on in order for some response to occur. It's probably the simplest way to do it. And stress does happen. It happens in all of our products. And in some cases, and eventually for all cases, the stresses applied to a product will cause it to fail. And that's not a bad thing, right? It's what happens. And I like to joke that it's what keeps us in business as reliability engineers is that things fail. And it's when they fail earlier than expected or unusual ways that they fail unexpectedly, that's what we want to deal with, and we want to ferret out and sort out and get rid of. Now, there's also this notion that we can apply stress to something to find what the problem is. And we use that in HALT, for example, or what I call discovery processes, where we apply a range of different stresses and sometimes combined stresses and find weaknesses in a product and determine what the margin is and so on. So we're actually causing failures to occur to learn something. And that's also a good thing. Now, stress screening is a different animal, and it's a different thing that we're gonna talk about a little bit. And what I mean by stress screening is that we're going to apply a set of stresses or a test, and we're going to try to sort out which are the defective products out of the population, and essentially get rid of the bad ones if we can, or repair them if that's practical. And so it's not a design for reliability type thing. They're often implemented in manufacturing processes or at some stage later in the production of a product. And they're, well, I'll leave it there. There's a lot of good and there's a lot of bad about them. And we'll talk about that as we go on here. All right. And I'm trying to mute a phone line that just dialed in, so bear with me for a second. Mouse is not working. Huh. Well, anyway, we'll see what happens. So please use the chat window here. Here's just a quick quiz. We often use temperature or elevated temperature to stress a product or a device of some sort. So what are some of the ways that increasing temperature can cause damage or can cause change to a product? I mean, I'll throw out there melting is the most common one, right? We raise a high enough temperature, pretty much anything is going to melt. But what else can temperature do besides melt a product? Yeah, thermal expansion. Coefficient of thermal expansion is something to be aware of. Thermal vibration. Khalid, you mean like thermal cycling, or vibration meaning much more free? Or I'm not familiar with that. I'm thinking thermal cycling, but that might not be it. Yeah, connectors may open. The difference in motion will cause it to create an open, or vias oftentimes will crack if they move too much. Yield strength, oxidation, corrosion, molecular creep. Um, yeah, I mean, electromigration is one that's pretty And Kyle, you're right. When we increase temperature, it vibrates, right? It moves, it expands, and gases will expand, pressures will go up in more solids, and we also get more. That's what temperature is, right? Is a motion. And some things will cure too fast or not well enough. Others will cure quicker. That may or may not be a damage-related thing. Uh, but there's, you know, quite a few different things that can happen when we just increase temperature. Now, let's keep that in mind because if you're going to increase temperature of something, it affects everything in the box pretty much, right? Same with most of the stresses that we can apply. Yeah, dendritic growth, Ken, is one of my favorites, it's, at least for photos of what can go wrong. Some of those images are stunning. The issue is that when we apply a stress to a product, we generally, in stress screening in particular, have a particular failure mechanism that we're interested in identifying or finding if it's present or not, or exciting or illuminating is probably the right word. Yet that same stress, whether it's temperature or pressure or mixed flowing gases or vibration or whatever, will also cause some form of stress or acceleration or change to a lot of the other elements of the product. So there's a trade-off there, right? We're going to cause damage on our entire product level if we just elevate the temperature looking for a temperature-related issue. So it's not near as straightforward as, well, we just raise the temperature and do a burn-in and it's all good. No, well, it also causes problems. I think that's my main point. Well, let's back up a little bit. Here's a few slides on what is stress screening and why do we do it, right? And what's the point of doing this kind of thing? And I'm going to say it's a necessary evil. Is probably it's the last resort. It's something that we can do if we have to, if there's not any other options. We'll talk about that again in a little bit. But the idea is that we're going to, if I get my cursor to move, we're going to apply a stress, much like we would do in an accelerated life test, in order to get something to happen more quickly. And in this particular case, what we're doing is we're trying to find a defect that's in a product or a component or a material. Oftentimes in stress screening, we know it's there. It's just that you can't see it with the naked eye. We don't have another way to identify the good from the bad. We pick up two drill bits and they both look perfectly good, but if we apply a little bit of force, lateral force to the edge of the tip, it may reveal one that has a crack in it and it snaps off or the crack becomes visible, for example. This is a quick example. And so we can accelerate the appearance of a fault or a failure. And the idea is that it allows us to basically design an accelerated life test that makes the anomaly or the fault or the defect in some part of our population visible, and so that we can either toss it away or repair it or do whatever. But that's really the point of doing the accelerated stress. If we don't do anything and we just use the product, those ones with defects in them are going to fail at some point, and they may fail sooner than we really want them to. And so we're doing a test or a stress screen in order to eliminate those faulty ones from the population before they go to customers. The rest of them should just work for a long, long time. Whereas the ones that have these latent defects in them, this is a technique for us to uncover them and identify them. And so we use an accelerant, a higher stress than normal, as a way, like in accelerated life testing, to actually cause it to happen fairly quickly. It doesn't do us a lot of good to put our entire inventory into testing for a year to find out which ones have a problem in it. That would be very, very expensive. It's probably not unheard of, yet it would be a pretty extreme condition or situation. The other part is that if we're setting up a stress screen, we almost always, and I would highly recommend that you do, have a specific problem in place. So for example, if you've got circuit boards and you know that some of them, but you don't know which, and it's not visible by another means, have some form of contamination that will cause your product to fail fairly quickly in the field. And so we don't want to ship those products. And we know it's corrosion. And so if we apply a little bit of stress, maybe power the boards and put a little bit elevated temperature, or whatever the conditions are for that corrosion to occur, we accelerate those conditions, that corrosion will occur faster. And we're able to identify which ones have the problem and clean them or get rid of them. Whereas the products that have no contamination on them will still see the stress, but they won't grow the corrosion because the initiating element, the ions, for example, or some contaminated material, is not there. And so when I say a specific problem, it's a very specific subset of the products contain some issue that we want to deal with. And it's one of the, I'm trying to think if I have it on the next slide or, no, let me go back here. So one of the things, let me get my drawing tool up here. I saw this drawing years ago, and if I actually have a pen, that would work, all right? So let's say this is a time, and I'm going to make basically a hazard plot or histogram of what's going on. And on our normal product, let me change my color here to some happy color. We're going to have some low probability failure, and then over time they start to wear out, and eventually all of them fail. And if we're good at our design and our manufacturing process, this is well after the warranty period or the useful life period or a period of time that we expect the product to be used. It's at some point in time that the onset of its wear out or failure is well off into the future. And so that would be for all causes. We have some relatively low failure rate, and at some point in the distant future, they all start to fail. Well, every now and then, and I think many of you may know this, and I'm not going to put you on the spot, is that we have a vendor batch that's bad, or a defect of manufacturing process, or we've got some error in the assembly line, or we have some dull tooling that affects 1 in 20 of our products. And it could be pretty much anything. But the idea is that there's some subset of our population that has some defect, right? If everything has the defect, no amount of screening is going to find which ones are good and which ones are bad, because they're all bad. Your stress screening will pretty much destroy everything, right? And so let's say I have this group right here, and it's going to cause failures well before the period of time that I'm interested in here. And so what I want to do is accelerate this group so that they get removed from the population. And looking at this a slightly different way is you may detect this kind of behavior if your field failure rate is showing a declining failure rate, right? I got a bunch of failures up front, and as those work themselves out of the population, my overall population is still there and humming along just fine, but I have initially a relatively high failure rate, and if I wait 3, 4, 5 months, it looks like it's coming down pretty quick. And that can be deceptive as to what's going on. So keep in mind that it very well may be that you have a subset of your population that has a defect that's showing itself in the field, and that you want to eliminate those as easily and as quickly as you can. And that's the basic idea. All right. For the person that just dialed in, if you could mute your line, I'm getting a little bit of static on that, and I'm not able to do that from my end of it. I'd appreciate that. All right. So the underlying problem here is that we want to accelerate something, but it has to be something we can detect. If you just apply stress to a product, say temperature, right? We're going to, yeah, and Pete, counterfeit parts is a good idea here, is we may end up applying stress to something that's just going to accelerate the primary defect, right? It's just going to accelerate whatever is going to happen, and it shifts the onset here earlier, and it shortens the life of our product. And so that's going to happen to some extent anyway, as we apply stresses to get rid of and identify a particular subset. And that's the trade-off, right? But the underlying issue here is that it has to be something that we know about so we can apply the appropriate stress, and it has to be something that we can actually detect. It doesn't do us any good just to heat it up for 100 hours and hope it makes it better, unless you specifically know that annealing is a part of your process for making your product. Right? If that's not the case, just adding heat and hoping it sorts out the problems of your product is kind of folly in my mind. So you should have a specific problem that you can detect and enough understanding of it so you know which stresses to apply, whether it's temperature or vibration or strain or whatever. But understand that problem very, very well so that you can apply the appropriate amount of stress for the appropriate amount of time such that you have a high probability of catching and cutting off all the defects that you're interested in without too adversely affecting the overall population. So stress that, because I've seen way too many times where people apply a burn-in or a HASS or a stress test of some sort and don't really know what they're doing or why they're doing it. They just say, well, that'd be fun. Let's do that. Or whatever their rationale is. The last part, and I want to stress this over and over again today, is that it's a temporary fix. Inspecting inequality went out of fashion in the 80s, right? It doesn't fix or improve your product. It just sorts, right? We're just getting rid of the bad ones. We got, say, a batch of counterfeit parts in there. Yeah, Brian, yep, comes from Deming and others. But if we have a batch of counterfeit parts and it got intermixed with our overall system, but we know it's on the order of 10% of our products, for example, well, we may be able to find those counterfeit parts with the stress test, with the screen, and remove them from the population. And then once that process, that supply chain is rectified and we've gone through that inventory and we don't have any risk of this counterfeit faulty part left in our system, we end the stress test. The stress test doesn't do us any good on good products. It's only good at finding the bad stuff. In general, hopefully you get the idea that I really, really, really don't like setting up and running stress tests. It's really not something we should go doing. And this is why, right? I know many of you have run into stress screening or you've done similar kinds of work, or maybe you've been thinking about it, but what could go wrong with the stress screen? And I probably have tipped my hand a little bit on this with mentioning a few of them already. Yeah, damage, perfect. Yeah, talked about that a little bit. Yeah, not using the proper accelerated conditions. I could over accelerate it or not accelerate it. And if I under accelerate it, I may think I'm finding, say, 1-2% of the issues, and that may be all I find, yet I've accelerated the remaining 5% that are going to fail even quicker now in the field. I have to go far enough to get rid of that subset of the population. Yeah, shortening life. Yeah, just setting it up incorrectly and causing collateral damage just in the handling, just on the setup, just on how the fixtures itself deal with it. All good. Yeah, reducing life. I think reducing life is a part of this process. It's a trade-off. Hopefully and ideally, if you can do it on individual materials or components before they get built into a product, you're in much better shape of not causing collateral damage. Um, but yeah, what can go wrong? It's too expensive. There's tons of them. Sometimes it makes sense to just throw it away and start over. Yet, as you know, if you're working in creating a product, that's not always an option. You have back orders, you got customer demand, you got a marketing rollout, you've got to put it on the shelf, otherwise you lose the market share. There's tons and tons of business reasons that want to get products out. And if but there's also that trade-off. If say 20% of them are bad, that's also not what we want to do. So how do we do both? Well, stress screening can be an option there to help you solve that. So here's some of the problems, at least the ones I thought of, and you talked about many of these already. The one that irks me the most is, well, we always do it. We build our servers, we put them on these racks, and we call it burn-in. It runs for 100 hours. We always do it. Now, what question would you ask somebody that always does the stress screening? What would be a natural question to ask them? Why? Usually that just gets, well, that's what we do, right? And it kind of goes into that circular argument. Why do we do that? It's because, and so on. I never worked with my mother either. But the idea is yeah, is the process this unreliable? Is the, I always ask, well, what failures are you finding, right? What is the stress screening finding for you? And in one case, they had been running the stress screen for about 5 years. They had found no failures other than one time a technician dropped the component on the floor and it broke it through handling. Um, they had not found anything for 5 years. And so it kind of begs the question, why are you doing this? What is it actually providing any value for? And they said, well, it makes us feel better that it's gone through the stress screen. We're not catching anything. Well, you've improved your process, you've changed technology, you've updated your assembly processes and designs such that this applied stress really isn't doing anything useful for you, and it's very likely it's shortening the life of your product unnecessarily. And so, yeah. And then, yeah, Greg, it's a good one. Is, what are you seeing in the field? What kind of defects are getting out there that this test is supposed to find? And if you're not finding any of them, is it the right test? Are you looking for the right things? Or is it even there anymore? If the only failures you get in your field, in the field data, are well after anybody really cares, and you hear about it anecdotally, either you've got a really, really good design system and screening system, uh, and maybe that's efficient for you. But it has to be overt, really thought out. It's not because we always do it. And for those that have attended many of these webinars, you may have heard this story. As I was doing a factory tour once, and we saw a technician take a piece of product, creating tens of thousands of dollars of scrap because the direction was to do this on the hour. And if she would have waited 10 minutes, she could have done it at the start of a batch and not created any scrap at all. But the directions were very clear, on the hour. And so we followed her to find out why this test was so important. And we saw, make a long story short, we found the records going back about 8 years that showed no failures for this test whatsoever. And we asked, why do you do this test? What is this test for? What are you trying to do? And what we found out was that the SAG test of this jacket material on a cable was designed and put in place for a previous generation of polymer that was closer to the margin of what was capable. And if the process wasn't tuned in just right, this test would find that it would melt the polymer, essentially. It wouldn't set correctly. It wouldn't bind correctly. And 8 years ago, they changed the polymer such that the melting point was way above what this test was even capable of experiencing or causing damage to. So every hour they caused scrap for 8 years just because that's what they always did. Nobody ever second guessed, what's this test do? What are we doing this for? Why is it here? Those kinds of things. So if you're doing a stress test, asking why, where's the data? Where's the data? How is this adding value? What's the end game? Those are all good questions to ask. Many of you already mentioned, and we've talked about, is that when you add stress, you add damage, right? It could creep or corrode or deform or melt or some form of damage almost always occurs. And it may be very small, it may not be a big hammer, it may be very small minor pieces, but cumulatively that all adds up to be bad for products. And then the one that's just bothersome, and it's similar to that story I had before, is nobody said, well, what's this test do? Right? Well, it looks for a design condition that we have very little margin on. Well, in that particular case, that factory tour I did, is they actually found a solution. They went to a different material. Unfortunately, they didn't close the loop and say, hey, quit doing this test. And years later, it was still running. If you put a screen in, it is because there's a problem. There's something wrong that you're trying to sort out and inspect out of your system. Is it a manufacturing variation problem? Is it a material supply problem? As one person mentioned, is it a counterfeit parts issue? Is it a design issue? What's the underlying problem that causes us to have some percentage of our products motivate us to do a screen and get it out of our shipments? If we're not solving that part of it, we're doomed to do the screening forever and suffer the consequences of it, not only the cost of the testing, but of scrap and rework and so on. Let's solve the problem, right? If there's a screen going in, there should be a parallel project implemented to go about actually solving the problem. Whether it's a design change, supply chain update, or a process improvement. It really doesn't make sense to me to put a screen in and then walk away and say that's fixed it. You know as well as I do, it's not a fix. It's not really solving anything. Yeah. Yeah. What would you do to go after the design? Yeah, nicked wire enamel. That's a hard one, and I see that also in inductors. Wire wound inductors is that nick occurs. It's a hard one to ferret out and find. It's much easier to put gloves on operators that are handling the wires, or to make sure you have no sharp edges that the stuff touches to nick that wire. But do some preventative work. What's the nature of that, the source of that problem, and where's it coming from? But that's the idea, is why are you doing it, right? And then what's it supposed to do? And then more importantly is, when is it going to end? What's our solution for this to get out of this thing? All right, so here's a quick quiz for you. If you were seeing a problem with your production, and so let's say 10% of the products had some detectable issue that you could accelerate and find it, where would be the best place to run that screen? Where would you locate the stress screen? My favorite answer by far, when I've asked this before, is in the person's office that caused the problem. Right? They made a design decision, they picked a supplier, they did whatever, but usually that's not practical. Also kind of gets into the blame game and punishment and stuff. We don't really need to do that. Yeah, Mark, very common sense, right? Get it as early in the process as you can. If we're dealing with one circuit board that has this particular issue, can we evaluate that circuit board before it gets built up into the rest of the product? Now, in some cases, you may have multiple types of screens going on because you have some inventory that already has it all built up, and it's not practical to remove the materials or components that have the potential fault in it. In other times, you may have the parts, the circuit boards, or the individual components, or even materials that you can do the screen. So when you're thinking through this, is where can I apply the stress such that it causes the least amount of damage to everything else. And oftentimes that's on a subsystem or on a component or on a material. And the further upstream, the better, right? If you're still investigating how this defect it gets introduced into your product, getting it closer to the source so that you have a less of a delay between when it happens and when you can detect it, it improves the chance of detecting what's causing the problem, right? Ideally, minimum is before it goes to the customer. Don't let your customers do the stress screening for you. That's what we're trying to avoid. But yes, early is possible. And if you can, if you're getting it from a vendor, let's place it there so that they can see and feel the defects compared to what they're processing. Maybe shorten that feedback mechanism that's going on there. That would be good. But actually, I was thinking about making that a trick question and saying, when is the best time to do a stress screening? It's like never. It's never a good time to do one. Is just make sure you don't have one. So let's talk about actually creating one. I'm trying to stay a little positive here. But then I dive right back into, no, let's not do it. So we have some fraction of our product has some defect in it, and we think we can inspect it out. Now, the first question really is, are there other options? And so let me open this up. What else can you do besides the stress screen? And we don't have a lot of information, but let's say we have a grinder, this handheld electrical power tool, and it's got a grinding wheel on it. And we know that 10% of them roughly have some defect in it that we want to eliminate. What could we do? What are the other options to think through? Right. So your boss comes to you and says, hey, we have to do a stress screen. You're the reliability person. You set it up. What other options should have been considered or should you promote as being options? What else can we do? Well, part of it, I think, Hassan, is that we do need to understand what's the root cause, right? So it helps us understand what stress to apply and where we can apply it. And Gregory, the functional test may not be able to find a latent defect. Let's say it's a cracked capacitor. A functional test is very unlikely to find that, whereas a little bit of vibration and thermal cycling will crack that capacitor all the way through and cause it to fail, for example. Or corrosion, a functional test will find the presence of too much corrosion, but not the initiating defects that are there. PHM. I'm drawing a complete blank on what that means, Jason. I want to say probabilistic health management, but I don't think that's the right phrasing for that. Yeah, DFMEA and other stuff like HALT and stuff we should be doing in the design process anyway. Prognostic health management. Thank you. Yeah. We could, if it's such a defect, that's a good idea, Hassan. If it's something that we can say, we can detect the difference over time and we can replace the unit in the field versus take it out of production. We can still get a couple months of use out of it or 6 months of use on it, and we can monitor the ones that need replacing. How about just throw them all away? Right? Throw the whole batch away. That's kind of an extreme. We know that 10% are bad in this 150,000 units we have. Throw them all away. Don't risk the chance of warranty and bad press and everything else. Just toss them. Another is to just ship them and increase our warranty reserves. Right? Kind of the two extremes. Monitoring, sampling, is it really a problem in the field? Is it not? If there's uncertainty, what's the underlying problem? What are we really dealing with? We have to do those anyway to make a good decision. But a lot of the stuff you're mentioning here is to move it upstream to avoid the problem in the start. Now, problems do creep in, and they happen even in the best of programs. So we always have other options, right? We can scrap it all, or we can ship it all and hope for the best, or we can do something in between. The batch and hold process is maybe some batches are worse than others, and do a sampling first and then do a screen if we have to, right? Um, if we don't yet know which line it's coming from or where exactly the defect is introduced, we may be able to use this idea that Brian's brought up, is batch and hold, do a batch sampling. And if it's got too much of a problem, say it really is at 10% of this batch is bad, then we do 100% inspection. If it's, say, less than 5% are defective, well, that's on order with what we normally ship anyway, so we're going to call that batch good and release it. And so it really depends on how many defects is too many for your particular circumstances in making this decision, and how rigorous you go into it. So a couple of good ideas there. The underlying thing we need, in the root cause analysis goes to the heart of it, is understanding exactly what the failure mechanism is. It's what you want to find. What's the initiating elements that are present, whether it's a crack or a bit of contaminated material or improperly cured adhesive. What are those defects within those structures that we want to actually find? And then it's understanding the failure mechanism, understanding the true root cause is usually enough for us to figure out, well, how to measure it, how to stress it, how to accelerate it. And the hard part here is that if you start getting too narrowly focused, you may focus on one failure mechanism and miss the others that are similar, right? That are very, very close to the same failure mechanism that would be likewise accelerated, maybe orders of magnitude faster, and so you cause a lot of damage. So it's understand the failure mechanism of the issue you're dealing with, what's causing your products to fail prematurely, but also what are those other failure mechanisms related to the stresses or the style of stress screening that you want to do. What other mechanisms come into play? And that's where it gets tricky. If I just increase heat and I can really accelerate the growth of the corrosion, but it also melts the case, well, that's a problem, right? I have some boundaries or limitations there, kind of an obvious one. And then once we understand the failure mechanism and how it works with, then we want to find a stress that accelerates as best we can just that mechanism. Now, that's not always possible. So that goes back to that previous comment. If once we apply a stress, what else does it cause damage to? What else does it affect? And it doesn't do us any good to weed out 10% of the defects to cause 20% more defective products. So really, really think through that and make sure you get it right. And then the last step in setting up a screen that's effective is to make sure it actually works, right? If you take 10 products that have 5 of them you know have, or you highly suspect have this defect in it, or you cause it to have that defect in it, because that root cause analysis allows you to really understand what causes the defect, and 5 that don't. You run the screen, and do you find 5 and the other 5 are fine, right? Do you find the right ones? In other words, how good is the screen at actually finding what you think it's finding? Another method, and we use this with HALT and HASS, the highly accelerated stress screening, is you run the screen 20 times. And you want to do it on something that has a good product, you suspect is a good product. And if you get no failures on that good product, after running the same screen over and over 20 times, you're relatively, not guaranteed, it's usually not done with enough samples to make any statistical claim on it, but that you're damaging everything else very little, and so that you're consuming less than 5% of the life of the product is at least one way to interpret it. What I tend to rely on is that you really need to understand the underlying root cause, the chemistry and physics of what's going on, so that your applied stress works well to identify and illuminate the problem and not damage everything else. And so running some proof of that before you run it out to your customers is probably a good idea in many cases. Okay. So this one shouldn't be a trick question at all now, but when do you stop a stress test screen? As soon as you possibly can. Okay? Ideally before you start. Find another option to work this problem out. If I can detect the problem through inspection without applying stress, I would much prefer to do that. So if I could get it an alteration to our functional test that I measure this variant of capacitance that indicates there's a problem, that would be great. It's not always possible. So applying stress and vibration and thermal cycling and so on is often the last resort. And then when do you stop it? Well, hopefully you are working simultaneously to fix the design, the process, the supply chain, or whatever, so that you stop contaminating your population with defective parts or products. And when those are worked through the system, stop the test. But my general advice is make sure you have a plan to stop it before you start it. All right, a couple of ways, and some of you have mentioned some of these already. The best way to do a stress screen is to not do it. And so next month, as a matter of fact, we've got two webinars. The one I typically do on the second Tuesday, I'm going to talk about process capability and tolerancing and reliability. So part of this process control part is to understand the stability of our products and working within our own supply chain and our own processes to make sure that they are capable of creating products in a stable, uniform, consistent way that work into our design information, tolerancing and design criteria well. We end up with a more reliable product. If we have an out of control process sending us all kinds of random dimensions and random material properties, it doesn't matter how good the design is, we're going to get bad products. So understanding the capability of your processes, and we're going to talk about next month in a bit more detail how that relationship connects. And I should mention the second one is by Stephen Wax. He's got a SPC and process control, process capability class on Ascendo, and he's going to do a primer on that and talk about the basics of kind of the 10 great tips in doing effective SPC. Keep in mind that it's not just a process control and yield issue. It really does impact the reliability of our products. Is when they're as close to dead center on the design as the better that will perform in the field. Now, of course, I'm assuming that it's a good design to start with. I've often found that in manufacturing, we can only make it worse, right? The product variation, the material variation, the assembly variation just makes products behave poorer in the field. So understanding that and incorporating it into the design process is a critical step in making robust products. So we can handle the variation that is going to exist. Yeah, Bonaventure, good question. I'll leave that one out there for other folks to answer. Yeah, if you're doing it by a third party, it's a step removed, right? So you don't really see what's going on, and they may not fully understand what it is you're trying to evaluate and how to evaluate it, the anomalies or the things you're looking for. So if you're going to do a stress screen, it usually takes a lot of oversight to get it right, to make sure that it's doing what it's supposed to do and not doing what it's not supposed to do. But if you're getting false failures, essentially, like handling, that's a whole separate issue of managing your vendors and the test processes itself. Good comment, though. Good question. The other part is design for reliability. Just all the stuff that we talk about in general of influencing the design is making sure it's robust and that it fits within the capability of our manufacturing process, that it's going to work in the environments and that it's going to be transported in and installed in and used in and so on. Let's think through all of the elements of getting a good, solid, robust design. And that includes our supplied parts and supplied systems and supplier and contract manufacturers. Those elements need to be incorporated into our design in order to get a reliable product. And then one other part is vendor management. I was working with a client the other day, and I asked them about their power supply, and it was just a brick. It plugged into a tabletop device and provided a low voltage power supply for their system. I said, do you want to evaluate your power supply as part of your reliability program? And they were adamant, no, it's store-bought, it's off the shelf, it's been around forever, it'll just work. Now, you and I both know that that's not always true, right? It doesn't matter to the customer if the power supply fails or if your circuit board that you're powering with that purchase part fails. Your product doesn't work. And so you still need to pay attention and ask the right questions, and if in many cases then understand the process control, the design robustness, the reliability aspects of a purchase part like a power supply. All too often, if you assume that it's good and drive merrily on, you may be surprised. It's not 100%, but it's often enough that it's become a problem. Sure, you love focusing on the area that you designed, but your product can fail for stuff that other people designed just as easily. And it's oftentimes that interface between the two of them that cause them not to work together. So evaluate them. Put that power supply into your regular routine of evaluating the robustness of your designs and your finished solution. So there's, all right, vendor management. I just drew a complete blank on what else I wanted to mention with that one. But a quick summary, if I have to admit that at times, in rare circumstances, and over much objection, I should say, a stress screening program is appropriate, right? There are cases where we just can't find the latent defect unless we apply some stress to it. And in those cases, and I would submit only in those cases, that we design an appropriate stress screen to find those defects and get them out of our supply chain, our shipments to customers. You got to make sure that the design of the screen is about as robust and rigorous as you would do in accelerated life test, because essentially that's what we're doing. We're adding an accelerant, a stress, to accelerate a failure mechanism, and that's what we do for accelerated life testing. So it's generally not trivial, and in many, many cases it's not obvious. So think it through. What are you stressing? Why are you stressing it? How does that manifest in the failure mechanism you're interested in, and not cause damage to other things, right? We got to make sure that we're not causing more defective products than we're eliminating from the population. And then end it. Please don't keep running a stress screen just because it's working. Fix the problem. Understand where that defect is introduced into your system and fix it. It's the only way to really make a robust, reliable product, is create a system that it minimizes the chances of these things occurring, and when they do occur, is you tighten up your design and your supply chain such that it doesn't occur again. And end the screen. A couple years ago, I ran into a vendor that was doing a burn-in, and it was part of their safety certification for their product, TÜV certification, included a burn-in for these rack-mounted systems they were building, these server-type systems they were building. And so when they first started up, they knew that many of their components and systems and so on benefited by doing a burn-in because there were so many connectors and so many issues that a burn-in actually did find a few problems on every day's production, and they were able to repair it, put it back in production in system, and it would test all right. And so it became a regulatory requirement that they do burn-in. And then they're realizing that the burn-in was just not finding anything anymore. It was spending 2 days of resources on all of their products and not finding anything. And it was ongoing for years. So they went back to TÜV and said, hey, look, we want to change our process. We don't want to do burn-in because it's not effective anymore. Our design is better. It's not appropriate anymore. And they had the data, they showed the information, and they were able to become recertified without that step being in the process. Now that was a more onerous process because of their certifications and the oversight they were getting from a regulatory group. In most cases, it's once you've identified that you solved the problem and it's worked out of your inventory, stop the test. Stop the test. All right. So I'm going to bring up the ending slide here. Let me see where it is. Including slide. It's got the links for the slide deck and a couple of links back to the site. And I just saw Growy. I'm not sure if I'm pronouncing it right. So consider the following situation. A low volume OEM buying circuit boards from a board fabricator for proof of concept product. The product is expensive and the first mission needs to be successful to continue the project. What would be a cost-effective way to protect against infant mortality due to process errors? Well, I don't know. What's everybody think about that one? Yeah, dial in your process, make sure it's stable before you start running. You can run less expensive components and systems and similar components to make sure you got temperatures right and solder is reflowing correctly and all those other things to make sure your process is stable, then go off of it. Yeah, if you're doing stress testing, it's expensive also, and yeah, and it's not a guarantee. If you don't know yet what your infant mortalities are, it's hard to know what stresses to apply or for how long. You may stop your test just such that it fails the first day, which is even worse in your customer's view. So yeah, it's a tough one, Grow. Well, it's also how well do you know your circuit boards and the process that they're using. How characterized is their process itself? I'd spend way more time at the board manufacturer's site understanding their process capability and controls. So not sure if that's perfect advice. See what others think of here. Yeah, good. So we've got a few minutes. I think you all know my opinion now about stress screening. It's a necessary evil. And hopefully you don't, well, maybe I'm hopeful that you got a stress screen that's running right now, and you're hopefully now asking better questions about, well, why are we running it? What's it doing? Is it set up correctly? If you run into this circumstance where you have a vendor calls and says, hey, we think 10% of our components are defective. Here's what we think is wrong with them. Here's how you can find them. And you realize you got 10,000 units already manufactured. That's a puzzle. How do you deal with that? How do you work with that? And I probably should have put in here is that the first step is really create a team and go figure out what you know and don't know, understand root cause, and so on. What are the options? But you may end up having to do a stress screen. And it is a valuable tool to have. Of course, though, in my opinion, it's one to avoid. But so a couple of ideas there for you. All right. And let's see if anybody has some comments for Growy, or if you have other comments or questions, I'll stay on the line and we'll see how it goes. Next month, we're doing tolerancing and process capability and reliability is what I'm doing. Stephen Wax is doing a presentation on 10 tips to improve your SPC, your process control. more details will be coming out on both of those. We really look forward to having those. I'm going to call August supply or SPC month at Ascendo Reliability. We're going to do a couple of things around that topic. And hopefully, if you pay attention to SPC, you won't need to review this webinar to figure out how to set up and run a stress screen. That would be great.